Moment we talk about relative velocity, there are 2-3 things which should come to our mind. And that's what we'll go through. I think if you recall last class, 2-3 things which come to mind. Relative velocity is nothing but vector sum of vector difference. Okay, and one of the two common cases are when the observer itself is under motion, and second case when object is moving on a moving surface. When object is moving on surface, just like this boat is trying to move. If there was river was not flowing, it was a lake. If the boat direction is like this, the boat would have reached here. But because if the river is flowing and this river velocity, boat is moving on a moving surface, the motion will take it downstream. So it will end up with the ground velocity with the vector sum of velocity with respect to the surface plus velocity of the surface. It's a vector sum. So to understand this point, this is what we discussed last time. And just look at this. I'm taking a question which is a little more tricky. And let's try and understand here. So what you're saying here, and this is something what you may experience may happen. So river is flowing towards east. So this is east direction. This is the direction the river is flowing at. And it's a speed at which the river water flows. As the distance from here increases, the speed of river also keeps increasing. So which means near the bank, river is flowing at a lesser speed. As you go toward the center, speed increases, which makes common sense also. So the speed depends on y coordinate, how far the point is from the bank. So at this point, lower speed, as you keep going, the speed keeps increasing. That's what this equation means. The speed of river is a function of distance from the bank. And boat is having constant speed of 10 meters per second in still water. Is road constantly aiming towards north? Road constantly, so constantly should be constantly aiming towards north, is starting from the bank. Find the drift it will have by the time it is 100 meters away from the bank. So we need to calculate drift is along x direction. What is the displacement in x direction? By the time it has displacement of 100 meters in y direction. That's what the question is. Let's try and solve this question. And this question I have taken up, this is something it helps you perhaps clarify your concepts even better. So how would the boat appear to be moving? This is standing. If the boat is aligned like this is velocity of the boat with respect to water. So had the water been still, this is the direction the boat would have moved. But because of river flow, it will also another velocity component get added. And what kind of motion it will have? If we observe from a helicopter, or if we observe from ground, this is how it will happen. So it has moved a distance y. It also has some displacement along x due to drift motion, and is like this. This is kind of path it may appear to be taking. And unlike when if the river velocity is constant, it would have taken a straight path. Here, what is happening? Y velocity in x direction also will keep on increasing. So this is kind of path river will take. Important point to note here is all figures I have drawn, the boat is always aiming towards north direction. So VBR is constantly along north direction. So displacement along y-axis is because of VBR, which is 10 meters per second. The velocity in y direction is always 10 meters per second, and x direction velocity depends on y coordinate. That's what the question is. So let's solve this question here. What we notice here, what does drift mean? See, if I talk of drift is nothing but displacement in the x direction. So if I take a small time interval dt, in that case, drift is display velocity in x direction into time. That's what the drift is. But only in this case, what happened, and what is Vx here? X component of ground velocity is only due to river velocity. By now, you should have understood y component is VBR, x component is river velocity here. VBR has no component in x direction. So the drift can be written as VR into dt. And when VBR is along y-axis, this is true only when VBR has no component. That's what drift is, okay, in a small time interval. Why I'm taking the small time interval? Because VR is not constant. That's why you write like this. Otherwise, if VR is constant, straight away you can write VR is into delta t. Okay. So since VR depends on y, we need to consider a small element dy so that VR may be taken as constant. That's what we do. River velocity depends on function of y. So different positions of y, when boat is here, it will have different Vx. Here it will have a different Vx. So y coordinate is changing. Okay, so when you have to calculate here, so when it is dependent on y coordinate, we need to take a small value of y, so that for that the small displacement velocity can be taken as a constant. Okay, so let's calculate drift when it moves from a point where y to y plus dy. It has a displacement of only dy along y-axis. So when y coordinate, it moves from y to y plus dy, displacement dy. What is the drift it will, or what is the displacement along x-axis it will have? That's what we need to do. So what is dx here? So basically this is dx here. So what we have, velocity we have written in form of y. That's the velocity here. That's what river velocity directly is substituted here, dx here. And there are three variables here, but x is changing, t is changing, and y is changing. We cannot have three variables for integration. So what we need to do, since we want to find out, we can integrate the, but why we need to use relationship between any two quantity. Y coordinate is related to time. What is displacement along y direction? Y direction displacement is VBR into t, which is 10 into t. So y, if we substitute 10 into t here, that becomes easy. Then I can easily calculate drift. Okay, so corresponding t, so time t corresponding to y, meter per meter in 10 seconds. So basically with this, what is the total time it will take to cross the river? What should be the limits of integration? So limits of integration, so simply I substituted in place of y, you substituted 10t. That's the expression here. When I integrate, what should be my limit? Limit should be from 0 to 10, because it will take, from this equation we understand, will 10 seconds to cross the river. So corresponding to y is equal to 100, t is 10. So if I integrate from 0 to 10, I get the displacement here. So this is slightly more complex question, and some of you just understand some of the basics. If it's like optional, if not everyone is not following, to the extent you follow, if you don't completely follow, perhaps you can keep this question as an optional question, not to be mastered at this moment of time. So you can keep it aside for a while. If you follow, well and good. So this is something again what will happen. And here one more thing you can do, some of you can also calculate trajectory. It's fairly simple. We can y and x both can be written in time. We can also calculate what trajectory the boat will follow. That's the second part of the question, which I'm not doing. Rest of you can do it. Okay. Now coming to another common question. So this is the case what we have dealt with so far. When object, which is a boat or swimmer or an aeroplane or person walking on an escalator or a travelator, when motion is happening on a surface which itself is moving with reference to ground. That part we had done. Now we are going to do a different part. So there are two varieties, so you have to understand both of them. Second common variety is RainMan. And we can have many, but this is something, is one example, and many things also can be similar to this. Let's understand here rain velocity observed by a man for his frame of reference. So what is VRM equal to? VRM indicates what the velocity. When we talk about rain velocity, actually we are talking about velocity of a drop of a rain. So any drop is like a point. Rain itself doesn't have a velocity, it has to have some particle. So rain velocity. So as seen from the man, VRM will be equal to VR minus VM. That's the equation we need to understand. This equation we know already. Let's try get an understanding of this relationship with a simple example. Let's see what the example is. So let's say this is the raindrop. Raindrop is falling vertically. If there's no breeze, there's no wind flowing, you can notice when there's a strong breeze, even when you're at rest, you can see the raindrop to be getting deflected in the direction of the wind. If there's no wind here, mostly raindrop will fall vertically downwards. So here raindrops are falling vertically downwards at a speed of 3 meters per second. And there's a man here who's vertically below the raindrop. Okay, what distance? The distance is each, perhaps each division is equal to 1 meter. So at a particular time t is equal to 0, man observes raindrop to be 3 meters above him. And if this man stays at the same place, he will see this raindrop approaching him, and raindrop will come and fall on his head. And if it, okay, and he may, so okay, fine. That's about how the raindrop will appear to be moving if man is at rest. Okay. Now let's say what happens if man starts walking at the constant speed of 4 meters per second. I have taken which direction it is moving towards left, or we can talk it some other direction also. It is moving towards left at the constant speed of 4 meters per second. So at t is equal to 0, he observes like this. What will happen at after 1 second? Let's see what happens. So after 1 second, so again in this case, what we had done, since motion in 2 dimensions are involved, I define unit vectors. Unit vector is what? Vertically downward direction I have taken as j cap. Okay, so j cap is vertically direction. Now, if after 1 second the man would have moved 4 divisions here, man has come up to here, man is at t is equal to 1 second here. So at t is equal to 1 second, where would he see the raindrop falling? Raindrop will fall at the same point. So he will notice here what is the position of raindrop at t is equal to 1 second. Then in man's frame of reference, this is where the raindrop will be. The raindrop will appear here. So to man, what will appear initially? Motion of raindrop as seen by this man in motion. Man is moving towards left. So initially at t is equal to 0, the raindrop would have appeared here. And t is equal to 1 second, the drop will appear here. So how would raindrop appear to be moving to this moving man? This will be VRM. And what is VRM here? Let's understand. That's how the rain. So if man start moving towards left, he will see the rain falling behind him by a distance equal to 4 meters, which is his velocity. And what is this VRM? It's a vector. I can express this vector plus this vector. What is this vector here? This VRM, this is VR, and this vector from here to is minus VM, because I'm going opposite to minus VM. So VRM is VR minus VM. So that's what we can, this is the same equation what we have written here, same relative velocity equation. This is just to get you an intuitive understanding of why does it work like this. So motion of observer tends to add equal and opposite velocity vector to the motion of man. So what has happened since man has started, you know what is happening here. What gets hit here is minus VM. So if he moves towards left, it is as if equal velocity is added in the right direction to original ground velocity. Thus, another way we can interpret this equation. So it adds another velocity, which is basically what is the VRM? This equation. What is added here? Minus VM is added. All right. So let's using this. So this is based on this what you call as vector polygon or vector triangle. Vector triangle. This is a triangle we can form, but many questions can be solved very, very simply using unit vectors in orthogonal system. And if you follow consistently, we can easily solve it. So I will solve a couple of 2-3 questions which are based on this. So let's see one by one. To a man walking at the rate of 3 meters per second, the rain appears to fall vertically. Is the rain falling vertically? No. Rain as seen by the man is falling vertically. So what he observes, whenever moving motion man observes, he is the observer himself. Coordinate system is attached to this person. Frame of reference is man. So what he observes is VRM. So VRM is vertically downwards. That's what first part of the sentence means. And if he changes his speed, what will happen? VRM will change. And VRM will change is magnitude as well as direction will change. That's what you should understand here. And let's solve this question. What is the speed of the rain? When he increases speed to 6 meters per second, it appears to meet him at an angle of 45 degrees with the vertical. So at this speed, it is vertical. At this particular, when he doubles the speed, it becomes 45 degrees from the vertical. What is the speed of the rain? How are we going to solve it? Only one equation. So all relative velocity questions are based on vector sum or vector difference. In this particular case is vector difference. VRM is equal to VR minus VM. Let's use that one. That's a equation you get to use. So first, use this equation rather than using in this form. We'll break it down into 2 components. We have to choose x-axis and y-axis. So what is, let's choose x-axis and y-axis. It makes our the problem simple. So we assume x-axis in the direction the man is walking, and y-axis vertically downward direction. Why we take vertically downward? So at least rain velocity, vertical component becomes positive. Okay. So what is rain velocity? We don't know. So rain velocity may have it will have component along x direction as well as y direction. So we assume the rain velocity to be ai cap plus bj cap. Whenever any vector we have to assume, we have to take both the components, unless we know for sure it doesn't have any component in particular direction. In this case, since we have taken y-axis to be vertically downward, b must always be positive. Rain cannot be falling upwards in ground frame, right? So this is what the case is. Let's take initial case. What are things which are given here? Initial, let's put those values. Simply, I'm going to use this equation only. What are things we know? V-man is walking the speed of 3 meters per 3 kilometers. So all units are in kilometers per hour only. Not change the unit. Vm is equal to 3 ia. And this is VR. So VRM will be equal to VR minus VM. So A minus, we can subtract I component to I component and the other one from B minus 0. So VRM becomes simply A minus 3 I cap plus B j cap. I'm simply using vector difference. As the rain falls vertically, what is given here? VRM is vertical. It means is I component is 0. That's what vertical means. Hence, this first part of equation or first part of sentence tells you horizontal component of rain velocity is equal to 3. So this is something important point, easy to understand. If the person walks with the same horizontal velocity as the horizontal component of the rain and in the same direction, it will appear to fall vertically to him. Okay. So we have understood now. Yes, Vignesh?
Sir, we can take the velocity of the man as 3 I cap or minus 3 I cap, right? Do we get the same answer both ways?
No. Basically, I have what I assumed here. What is x-axis I have assumed?
Okay, in the direction of the man.
Yes, that's why I think that choice of x is important. Okay. Okay, so this is VR. So I substitute this value. So I have one value here. So this is now, so before I go to the next step, my equation of VR becomes like this. Now we use the second part here. Second part, what happens? VR changes. Hence VRM will change. That's what we are doing here. What is VM in this case? It doubles the speed. Whenever it is not mentioned, we have to assume it in the same direction. Unless it is mentioned, here doubles in the reverse direction. Then I would have written minus 6i. Since it is not mentioned, we assume it is moving in the same direction. Direction does not change, only magnitude becomes 6i cap. Again, I write VRM. What is VRM? This is VR minus VM. I think it's very easy to find the difference of two vectors. 3 minus 6 I cap plus B minus 0 is A cap. So as the angle is 45 degree means this component and this component need to be, magnitudes have to be equal. 45 degree, now which direction it is falling. So this is something, so magnitudes have to be equal because we don't know 45 degree in which direction. So we can just equate the magnitudes. So it gives you value of B. Since this is equal to 3, this also has to be 3. B cannot be minus. I hope you understand why B cannot be minus. Okay. So we understand here B is not minus, and we can draw that also. So if I want to draw, what is VRM equal to? VRM equal to, say this is some this is I cap we assume, and this is J cap we assume. So answer comes to equal to 3 I cap. This is rain velocity. The rain is falling like this. So this is VR. How would this rain appear to be falling to a man who's moving with the speed of this? One division is equal to 3. This division also 3. So in second case, man is walking with the speed of 6i. So what will happen to him? He is giving an velocity up like this. So how would in second case rain appear to be falling? The second case VRM will be like this. It will make 45 degree, but to man, rain will appear to be falling like this. So it will be falling from his face. That's what it appear to meet him. It's not falling in. This will be VRM in the second case. And you notice what is VRM here? I component will be negative, J component will be positive. Why I component becomes negative? When we increase VR in X direction. In VRM, it equal to subtraction of that velocity. Okay, so this is how rain will fall in the second case. And if he has to hold an umbrella, he will have to hold an umbrella at an angle of 45 degree with the vertical. Okay. Now, a similar thing can come in form of what comes in form of rain. Wind also something similar. You might have noticed wind is speed. If wind is still, wind is not blowing. If you're riding on a cycle, it will appear that wind is blowing from your front. The wind will see you are riding towards north. To you, wind will appear to be blowing towards south. That's what happens in case of wind as well. Okay, there also what we observe, if we start moving, if you move in the car, when you move, so just imagine when you're moving in the car, okay, if he has sunroof, you stand from the sunroof, what you'll find, wind velocity observed by a person in motion is different. What you observe is wind velocity with reference to man, VWM. Okay, let's solve this question here. A woman is traveling north at 100 kilometers per hour. find the wind appears to blow from west. So whenever a person is moving, we'll not say wind is blowing from west. Wind is blowing from west in that frame of reference, thus apparent direction. And when movement travels her speed, the wind appears to blow from northwest. This question also, I'm doing one more question, which is almost identical to previous question. So in this case also, let's solve this question. This case, entire motion is happening in the horizontal plane, unlike previous case. That's the difference between RainMan and WindMan kind of question, or woman also. Okay, so let's see here. So you mark this direction, and we can assume this direction is I cap, and north direction is J cap. So let's solve this question here. Let's assume x-axis in the east. So I have taken here W, there's wind and woman. Both start with W, so I have elevated this moment to the status of a lady. Not elevated, maybe fair to call lady only. So what does WL indicate? Velocity of wind in the frame of reference of the lady will be velocity of wind minus velocity of the lady. Okay, now we have chosen the direction because vector, so we have to be careful about sign convention. So we must define sign convention before we start solving the question. Now, what is wind velocity? We don't know. We assume it has no vertical component, ai cap plus bj cap, which remains same even if wind velocity remains independent of motion of the observer. What will change only when it becomes relative velocity when observer starts moving. Initial case, what is the velocity of the lady? We have taken northward direction as j cap, so it will become plus 10 j cap. So what will be wind within the frame of reference of the lady? Is difference of the two. It adds a negative velocity minus 10j. So I will add minus 10j cap here. That's the equation. ai cap plus p minus 10j cap. Now we'll use the condition here. It appears to blow from northwest. This is north, this is west. So wind will appear to blow from northwest, means this is how the wind will appear to be blowing. So which is the direction of wind then? If it appears blowing from northwest, this is the direction of the wind. So direction of wind is, it will be, this is wind direction. So it will have a positive I component, it will have negative J component when it is blowing from northwest. Okay. So in that case, what we get as B as sorry, what I'm saying now, please scratch that one, is blowing from west. So it is blowing from west, wind will appear to be blowing for west. It means wind direction in that frame of reference is towards east. It means it has no J component. So J component will become 0. So it gives you B is equal to 10, very similar to previous question. Now, second case, what happens? Okay, now we have found the value of B. We'll substitute the value of B here. That's the wind velocity. Let's solve the second part. Yes, Abru?
Nothing, sir.
Okay, let's continue. So what happened in other case? Now it doubles her speed without changing a direction. So velocity of lady will become 30 j cap. Velocity of lady becomes 30 j cap now. So what is VRM here? VRM is again, so add minus 30 j cap here. That's another way of thinking. That's what we do here. So A I cap plus 10 minus 30 j cap. So as wind appears to blow from northwest, this is how the wind direction will be. It will be at 45 degree. It's blowing from northwest. This is wind velocity direction. This is 45 degree, which means I component and minus J component are equal. J component in terms of magnitude, both are equal. So this magnitude is 20. A also has to be 20. So very similar to previous question. So I have done this question so that we understand one case motion is happening in a vertical plane. This case motion is happening in the horizontal plane, but approach of solving question remains identical. So it's nothing but vector sum, vector difference. We choose a coordinate system and consistently apply that coordinate system, we get our answer. Okay, that's how the wind direction will flow. Now, I will just do for the some of you may feel necessary this question also. What happens if man is walking on an inclined plane? Approach doesn't change. So just to prove that even these questions also are not difficult, if you follow step by step, same way you can get an answer. So let me do that question also. Okay, okay. So when a man moves down an inclined plane with a constant speed of 5 meters per second, which makes an angle of 37 degrees with the horizontal. So man is not walking on a horizontal surface, he's walking on an inclined plane. And this inclined plane makes a angle of 37 degrees with the horizontal and moves down. So what is the direction man? He's moving down. and rain is falling vertically. He finds rain is falling vertically downwards. Is it the real speed of the rain or is apparent speed of the rain? Of course, he finds, a moving person finds, so VRM is vertically downwards, first case. So let's convert it into a form of vector values. VRM is equal to VR minus VM. Let's assume the axis as shown. So I have taken x-axis, this is x-axis, and this is y-axis. Rain falling, mostly I prefer to have y-axis in the downward direction, so that I know y component is always positive. Y component always should become positive. B must be positive, and if depending on V, the VR will remain same. VRM alone will change depending on motion of man. So this is velocity. Now, in case of what is the velocity of the man here? And the velocity is pretty simple. So it is walking at 37 degree. So let me take its component. X component will be equal to 5 cos 37 and Y component will be equal to 5 sin 37. So cos 37 is 4. So it becomes 5 into 4 by 5. This becomes 4 and this becomes 3. So I'm resolving. I hope most of you are comfortable. If not, practice that one. So VM becomes equal to 4 I cap minus 3 J cap. Hence VRM. So on this, we subtract this A minus 4 I cap plus B minus 3 J cap. It appears to be falling vertically downwards, means VRM is in the vertical direction. It means it has no X component. It has no horizontal component. So it gives you A is equal to 4. Similar to previous question, nothing new we had done. Now we have a second part. What happens now? Second part, the man now comes to second part. He moves up the inclined plane with the same speed. Now the man is moving up. No, you may, some of you say, why is facing downwards? I had same image, so it is moving upward. Okay, and moving the same speed, 5 meters per second. Now what will happen? So let's see that. In that case, no X component. So what would VR be? VR will be, sorry, I missed minus point here. Okay, so sorry, rain velocity, we got rain velocity is equal to AI 4I plus BJ cap. We got 4 from here. Now let's write what is VM. See, when in this case, it is reverse direction. Whatever velocity I had, either I take components or simply add a negative sign. It is opposite in direction. So it becomes, earlier it was 4I plus 3J, it becomes minus 4I minus 3J cap. So again, I take the difference, that's VRM. Because information is given, he find the rain makes an angle and so and so. So to use this condition, I need to find the value of VRM. So we find VRM, this minus this, so actually it will add up. 4 minus minus 4, 8I, and B minus minus 3 become B plus 3 J cap. So this is the equation here. So let's use this equation. What does this equation mean? It has certain X component. So what we find X component here, and we find Y component here. And whenever you have X and Y component, angle made with the horizontal, tangent of angle made with the horizontal is Y component divided by X component. So that's why I'm going to use. We find the rain makes an angle of, basically it's given tan theta is equal to 7 by 8 with horizontal. So this is nothing but Vy by Vx. So tan theta is equal to 7 by 8 is equal to Y component divided by X component. So I use substitute this value, find the B value is 4. So that's a very simple, I think all 3 questions what I have done, all are almost identical approach. Having done 3 questions, and anybody has difficulty, you go through that again. I think you should not find any problem solving questions like this. All relative velocity questions so far, very straightforward application. Now move on to something else. There's other applications of concept of relative velocity. So I'll explain the concept of velocity of approach, and fairly simple thing. So let's understand velocity of approach. If this takes simply a particle, if moves in a circular path with O as center. So I'm taking this is something O is a center, and there's some particle which is moving in a circular path. The distance between them does not change. So distance between O and P will not change. Distance between them will not change. So at any instant, if velocity of P, so what I understand, this is easy to understand, the distance between two parts, center and P will not change. So I'll generalize this statement, distance not changing means what? So I can say, if any instance, if velocity of P is perpendicular to the line joining O and P, then instantaneous velocity of approach is 0. What does velocity of approach mean? Velocity of approach is rate of decrease of distance between 2 points. So if the distance is r, this if velocity is perpendicular, instantaneous rate of change of distance for a very brief period of time, it will move from here to here, very small distance. How much distance? Negligible distance. Both points are equidistant from O, so distance will not change. and we have understand velocity approach, rate of decrease of distance. So what does rate of decrease of distance mean? So I calculate distance after the motion, and I calculate distance before the motion. And this is the change in distance. If I divide by time, that's the velocity of approach, rate at which distance is decreasing. Okay, increasing or decreasing. So velocity of approach, rate of decrease, and velocity of separation, distance is increasing. So what I understand, the if I join these two lines, perpendicular component does not lead to velocity of approach. It doesn't contribute to velocity of approach. Okay, let's take this case here. So here one was moving in a tangential direction. So let's take a case if O is like this. At a particular instance, point P has a velocity V, which is an angle alpha with the line joining them. So now if P moves in a small time interval, though I'm marking this point like this, but it will be infinitely close to this. Now if P moves from here to here, what I notice here, compared to original distance OP dash distance is smaller. Is smaller by how much? How much it is smaller? If I move a distance this one, so basically even how much is the distance is smaller, and what is the rate at which the distance is decreasing? If I have understood this concept, we can easily apply here. Let's see how do we apply that part here. What is the velocity approach? What is the rate at which distance between point O and P is decreasing? We express velocity into two components. One is perpendicular component and second is the radial component. This component will not lead to any change in distance. This component only will lead to change in distance. So velocity of approach is only the radial component. So in this case, what is velocity of approach of P with respect to O is V cos alpha if angle is alpha. O is at rest. Okay, that's the velocity of approach. But will this, if the particle P keeps moving at the constant speed, let's see, it keeps moving on. If initial distance between O and P is L at time t is equal to 0, so at time t is equal to the distance is L, then at little time later dt, the distance will reduce by V cos alpha into dt. That's the significance of velocity of approach. Distance will be how much will the distance after time dt? It will become velocity approach. Basically, distance is equal to velocity into time. But here, which distance we're talking about? So it moves to this point here. Initial distance was like this. And after time, small time dt, we have measured this distance. And this distance will be shorter by how much? V cos. And you can easily understand. This distance will be equal to V dt. Reduction is distance is equal to, we take this component along the length. It will become V dt into cos alpha. That's the velocity approach. But as the particle keeps moving, okay, keep moving with the constant velocity, what will happen after some time the point reaches here? So a little later time, even though V continues to move in the same direction, now what will happen, even the velocity is same, the angle alpha will change. So velocity of approach will not remain same because angle alpha, as it keeps moving on the straight path, angle between, what does the angle alpha mean here? Angle alpha between radial vector, which is joining instantaneous position of P with O with the velocity vector. What is angle alpha here? Jaideep, what is angle alpha here?
It is the angle between the radial vector and the velocity vector.
Right. No, and will it, you understand it will keep changing?
Yes, sir.
No, so velocity approach is instantaneous value, it will keep changing. That's important point you have to keep in mind. Okay. So if it keeps moving here, so suppose it keeps moving here, this path will take. And we notice when it is here, the angle becomes larger and larger, and it will keep changing. We'll use one more important concept here. If point P is moving the velocity V at an angle alpha, initially, line joining through is like this, what would be the minimum separation between O and P? So Jaideep, can you also answer, if this angle is alpha and P has constant velocity, what would be the minimum separation between O and P?
It will be when V cos alpha is maximum.
No, think of again, what is the minimum separation? See, as compared to this point, when it is come to this point, is the distance reduced or increased?
Reduced.
Here?
Further reduced.
And by the time it reaches here?
Yes, sir, it becomes minimum.
So where would it become minimum? How would distance, where would distance become minimum? How do I identify that condition? Let's see very simply. The distance, it is moving along this path. So basically distance is a distance of any point in the line from O. When will the distance of any point on the line from O be minimum? When we drop a perpendicular. So if I drop a perpendicular, this would be the minimum separation between O and P. Is this difficult to figure out?
No, sir, understood.
So this is the minimum distance. So if motion is along a straight line, the distance will be minimum that any point in the straight line, which point will be minimum distance from O. So when you drop a perpendicular, length of the perpendicular is minimum distance of the straight line from point O. And how about if the minimum distance is equal to, if length is L, velocity makes an angle alpha, minimum distance is L sine alpha. That's a minimum separation. And what time it will happen? It has to travel a distance equal to S cos alpha before the distance becomes minimum, and to travel the distance L cos alpha, time taken will be equal to S cos alpha by V at this time. So this will be the value of time when the distance will become minimum. So we are understood both the things. I hope this part is clear. Velocity of separation, it helps you find minimum separation. It also helps you find at what time will the separation becomes minimum. Yes, Vignesh?
So when we take velocity of approach, why will we just calculate, why do we always calculate the rate at which the radial distance decreases? Like not the overall
See, when
distance?
we are talking about distance between 2 points, we are talking about distance. So when this, see, point is here, if the point P moves from here to here, P dash. Because sometimes distance is also important. How come from O compared to initial position, am I nearer or farther?
Nearer, sir.
Nearer. So at what rate is my distance from O reducing if I want to calculate? I have moved a distance. What is the distance if I make it very small? This distance is equal to, what is this distance? This distance is equal to VD. But when I move this distance here, how much closer I have come? So when closer I have come, at displacement, I can take in two components, tangential component, which doesn't reduce the distance, the radial component. How much is the radial component? V dt into cos alpha. Okay. And why we are doing this one? It becomes useful. It has certain use here. We want to understand. We are not interested in velocity. We are also understand how the distance between 2 points are changing. And sometimes it is useful. We'll see how it is useful. It is useful in case of constraint motion. It is useful in solving numericals. It is also useful for getting marks in the competitive examination. That's why you understand velocity of approach. So have you understood what are things you understand? If particle is moving, so there we can resolve velocity two components at an instance, a perpendicular component and radial component. Which components lead to change in the distance, reduction or increase in distance? The radial component. The tangential component does not contribute for a very brief period of time, does not contribute to velocity of approach or velocity of separation. Right. Okay, that was something when one particle was at rest. Just assume. See, if you are standing here, one person is standing on the ground, and you're looking from the sky. So one person on the flat ground, one person is here, and it can be any particle. There's another particle B here. Both start moving. If I draw the path here, what I notice, of course, their path will cross. If their path cross, does it necessarily mean that they will come and collide here? See, their trajectory. This is a trajectory of A. This is a trajectory of B. If A is moving the constant velocity and B also is moving the constant velocity. So this is the initial position, and this is a line joining initial position. So initial velocities are, the velocities are constant, but compared with reference to initial line joining those two, velocities are making angle alpha and beta. What is velocity approach when both are in motion? Again, instantaneous. This may change as the position will change. What is instantaneous velocity of approach when both are in motion? We can find in this case, again, when two objects are in motion, we can effectively make one object at rest if I choose that object as frame of reference. And we other particle, what? In that case, we have to change the velocity of other particle. In that case, what will the velocity of other particle? It will have a velocity equal to relative velocity. It will have acceleration equal to relative acceleration. Let's understand that part. So for in the frame of reference of A, so if I assign a coordinate system to A, B will appear to be moving in the velocity equal to VBA. And how do we find VBA? VBA is nothing, VB minus VA, vector difference, take the components and take the difference. Using relative velocity concept, the problem becomes equivalent to one object at rest and only one in motion. So this particular problem gets reduced to something like this. So once I find VBA, I can find this direction also. So this question, both particles in motion, is reduced to a question where one particle is at rest, other particle moving in the relative velocity. So just think of it, what it means. If you are in space, see, when we move on Earth's surface, we figure out based on surrounding whether we are in motion or something else in moving. See, some of you might have seen that one. If you are traveling in a train, if you are looking at the train standing next to you, if other train starts moving, you get an impression as if your train has started moving. Then you look at the platform, you notice, no, your train has not moved, and you figure out other train has started moving. So this is something, if other objects are not around us, it becomes difficult to comprehend. So if we just suppose this is spacecraft is moving in space in a horizontal plane, horizontal plane has no meaning, it's moving in a plane. This object is moving like this object is moving like this. So if you are like Captain Spock or whatever, I think you're sitting somewhere, if you are sitting in aircraft A, you will not know what speed you are moving without the aid of any equipment. If you don't have any equipment, suppose you are sitting in the space, you will not know whether you are in motion or not. So when you're looking at B, how would B appear to be moving? In that case, it will look this motion, and suppose one case you are moving or B also moving, other case you are at rest and B is moving with the velocity equal to relative velocity. Both cases it will appear identical to person sitting in the space. That's what relative velocity means. It will appear identical. So one is that's a relativity concept. Okay, so how would motion of other particle appear to person sitting in the rest? This is what I think what we have drawn here. This is something person sitting in the ground. He notices A is moving like this, B is moving in this direction at a constant velocity. But to person A here, it will appear, okay, I am here. He doesn't see, now look in this, you see person B is moving this velocity. Okay. Let's take here, how do you find this velocity? You take x and y system, coordinate system, resolve those two velocities, find the vector difference, that's the relative velocity. Now, why this is useful? Once we have relative velocity, as we have seen earlier, it is useful whenever we have to find minimum distance between two objects. See, two objects are moving like this, the paths will cross. It doesn't mean they will collide. They may not collide. That's an important point here to understand. Even though they move in the same path, the particles may not collide. So what is the condition for collision for two moving objects? There are a number of ways we can define condition for collision, and pay attention. What is the condition for collision of two moving objects? If they have to collide for some value of t, but I assume they collide at time t, so what has to happen at time t? Both particles must have same position. So if this particle is moving, and this is the point where their paths cross. If A reaches this point at some time t, and B also reaches the same point at t, then only collision will take place. Both must have same position at a given time, at some real value of time t, then it will collide. What is other way to define the condition for collision? Using this concept of when both are in motion, if I take relative velocity, so if I observe motion of B in the frame of A, I place the coordinate system in A and I measure the coordinates of only point B. And that's what relative velocity means. So coordinate system is here, and this is constantly measuring the position of B. In that frame of reference, it will appear to moving like this. So when theta is 0 here, if theta is 0, if we calculate VBA and theta comes out to be 0, it means B will move towards A and come and collide. That's a condition for collision. VBA must be directed towards A. Same thing I can define in one more way in reference to this frame of reference. When would X component of VBA become 0? So what has to happen? Basically, sorry, what we are saying, the condition for collision is if I use this coordinate system, Y component of VBA should be 0. Then only theta becomes 0. What would make Y component of VBA 0? Y component is Y component of B minus Y component of A. If I take the difference is 0 when both have equal Y component. That's the third way of defining condition for collision. If we choose x-axis along the line joining AB, if we choose x-axis along the line joining A and B, then Y component must be equal. Y component means, that's why Y component doesn't mean any choice. Only if I choose x-axis along the two particles, then the components perpendicular to that must be equal. If perpendicular components are equal and velocity is a constant, it will undergo collision. So there are three ways I define collision. Okay, So far so good. Anish,
Yes, sir.
are you following so far completely?
Yes, sir, I'm following.
Vikram,
Yes, sir.
you understood condition of collision? Makes common sense.
Yes, sir.
But can you convert common sense in form of a mathematical relationship? That also is important. Have you understood this part also, why you converted two motion into single motion?
Yes, sir.
Okay, good. So if you understood, then you can apply some condition. So basically what you understood condition of collision. I will take up some question which will take up, use some of the things what you have done recently. So this is one first question, which is based on the similar concept here. All of you read the question and identify the condition.
After 2 seconds.
Yes. So basically, this question also is very simple. If they collide at 2 seconds, their position vector should be identical at t equal to 2 seconds. That's what this question is based on. So that's why I'm saying when you mark for revision, when you read this question, what should come to your mind? Immediately should come to mind. Let me find the position vector at 2 seconds for the first particle and the second particle, and both must be equal. And how do you find position vector? Displacement is equal to velocity vector into time, which is final position vector minus initial position vector, or I can using uniform motion. So okay, that's what you can use. Displacement is equal to, that's what v bar into t is equal to final position vector minus initial position vector, or final position vector is equal to initial position vector into velocity into time. T is 2 seconds. So to find position vector of first particle after 2 seconds, I multiplied this term by 2. So 4 into 2, 8 plus 3, 11, and 6 plus 5, 11. So I find position of first particle after 2 seconds, 11 I cap plus 11 j cap. Similar way, I find the position of the second particle also. In this case, it comes to minus 5 plus 2a and minus 3 plus 14. So it becomes 11. So these two are equal anyway. Only thing for them to collide, these two also has to be equal. And I can easily find value of a is equal to 8 here. Okay, fairly simple question. I hope all of you easily solved. Next question is slightly more tricky, and this is something of what we talk about here. Let's just read the question first here, and let's try and understand what does it mean. What I find again, so many people missing, 44 people only present. So I don't know what the trajectory is. If I want to understand, the trajectory may be somewhat like this. It has to turn towards left. And if I have to check whether trajectory drawn is correct or not, how would I check at any point? This is point P dash. Any point, if I draw a tangent here, and if I connect O to this point P to O, again, this angle should come 60 degrees. Then only it's a correct trajectory. So here also, by the time it comes here, that's kind of trajectory it has to follow. I hope this is understood. How is the trajectory drawn? Trajectory will be such that any point, if I draw a tangent, any point if I choose, at that point, I can draw a radial vector taking O as a reference, and also I can draw a tangent at that point. Tangent at the point gives direction of velocity. This angle has to be constant equal to 60 degrees. Do I need to know this trajectory? No. But do we need to understand this trajectory? If you understand, it's good. So Bhagyashree, have you understood what I'm saying here? What kind of trajectory?
Yes, sir.
Yes, how did he define the trajectory here? Can you tell Bhagyashree what are the words we can use to define this trajectory?
We can find that if the angle is 60 degrees always between O and P, and then we can find that it's a spiral.
No. So any point on the trajectory, if I draw a tangent, it will indicate direction of velocity, and I connect that point P to origin, that becomes radial vector, and two of them should be this two lines should make an angle 60 degrees. So this is something intuitively it makes sense. It will have some path like this. But what is important here? See, in this case, here, what is the velocity of approach? Here, the distance is decreasing at the speed v cos 60. Even here also, what is the velocity of approach, Bhagyashree?
60 degrees.
The angle is 60, v also is constant. So it is moving closer to point O. Distance between O and P is reducing at rate of v cos 60. That's what, so if I keep changing direction, if we keep the velocity magnitude is constant, and angle between position vector of P and velocity also is constant, in that case, velocity of approach will remain constant. So velocity of approach between O and P will remain constant. That will mean equal to 20 cos 60, which is equal to 5 meter per second. It means every instance I keep drinking, if this time is t here, it has come to point t here. So if I calculate this point O P dash, the distance has shrunk. If original distance was d, now the distance will be equal to d minus velocity of approach into time. The distance is shrinking. That's what velocity of approach means. Well, distance keeps reducing at this rate. Okay. So when would P, if I keep moving like this, will it happen at some point in time? The P will come and collide with O, will come and collide O. Since the distance keeps reducing, at some point in time, it will come and reach O. Question is how much time it will take to reach O. That is very simple. Velocity of approach in this case is equal to O will reach O in 20 seconds. Velocity of approach is 5 meter and distance is 100 meter. So in 20 seconds, it will come and meet O. So this is part the path it will take. I hope this part is understood, and this is something not so easy to follow, not so intuitive. Abhirup, is this understood?
Yes, I understood.
Now, this is the case, to maintain constant velocity, angle has to keep changing. This is a kind of trajectory. A similar question is given in form of a triangle, which is given, it has come in long time back in JEE Advanced. And since then, many books have given this question. And because it's a little difficult to follow. But conceptually, it is similar. Not in both are in motion. What is the question given? So let's say this is an equilateral triangle of side L. And sorry, what are you? Sorry, so there are 3 points A, B, C. A is always moving. A always moves with a constant speed V, and it is always directed towards C. A moves always maintains its direction aimed at C. C also moving always directed towards B. B is always moving directed towards A. Okay, and all are moving the equal speed, initial triangle and L is L. So when I look at this particular instance, what is the velocity, at what rate the distance between A and B is shrinking, A and C is shrinking? What is velocity of approach here? Velocity of approach, because of this velocity of approach is V, and because of this angle is 60 degrees. So it will also have a component equal to V by 2. Hence, these two particles are approaching each other with the velocity of approach V plus V by 2 is equal to 3V by 2. So because of both the motion, velocity of approach is equal to 3V by 2. Okay. Dhanshri?
Yes, sir.
Is this understood?
Yes, sir.
So distance is shrinking. But what will happen in a small time interval? C has moved to this point. Is it not? C is moving. It has moved to C dash.
Yes,
So
sir.
can the direction of A still be same? No. So by the time the direction of A also has to see direction, it has to keep moving. So direction of path also, again, what will happen? It will have this kind of path what we discussed earlier. As the C keeps moving this direction, so the trajectory will follow something. So the tangent drawn anytime should meet C at that instance. So this is kind of path it will follow. And even C also will follow this kind of path. And B also will follow this kind of path. And finally, what will happen? They will come and meet at centroid. So, and this question is one type of question, not too many variation. If you understand one, we will not spend too much of time because some people will take a lot of time to understand this. So, velocity approach is 3V by 2. Hence, particle, and when a particle moves here, at some point that this particle has come here. This particle also, if I draw the trajectory, this particle has come somewhere here, but it is a similar position with respect to this particle here. If at any instance, if I connect all these particles, what will form? It will always form an equilateral triangle. The shape of line joining 2 points will not change. Only thing what happened, the triangle size has shrunk. The size of triangle has shrunk. What rate the side of triangle is shrinking? Side of triangle is shrinking at the rate of 3V by 2 per second. And what is only shrinking, it is also kind of rotating. Thus what will happen? So 3 particles, if I connect all 3 points at any instance and keep watching how these points are moving, it will appear like a triangle which is shrinking as well as rotating in anti-clockwise direction. And rate at which side is shrinking is 3V by 2. If initial length of the side was L, which is shrinking at the rate of 3V by 2, which is called velocity approach, which remains constant with time, at what time will the side of triangle will become 0? It will become 0 at time t is equal to distance by velocity of approach. At this time, all particles will meet, or triangle will shrink to size of a point. And we can, a similar question can be worded in different forms.